Good afternoon, everyone. Welcome to the G.S. Beckwith Gilbert Class of 1963 lecture. I'm going to say a little bit at the end about what that is. But just for now, let me just say, for those of you who don't know me, I'm Vince Poore. I'm the Dean of the Engineering School here at Princeton. And it's my distinct honor and pleasure to introduce today's speaker, Tom Siebel, who's going to be talking to us today about new business ideation. So Tom is a longtime friend of Princeton. He's a former trustee. He's actually a Princeton parent. His son, Riley, is a member of the class of 2011. And I'm very pleased to welcome him back today. We'll have this opportunity to hear about his thoughts on this topic, which is a subject that he knows a lot about. So Tom founded and served as chairman of Siebel Systems, one of the world's leading software companies, which merged with Oracle in 2006. Today, he's chairman and CEO of C3 Energy, which harnesses the power of big data, smart grid analytics, social networking, and cloud computing to help utility companies improve safety, reliability, and efficiency of power delivery. I had the opportunity to visit C3 a few weeks ago, and it's really an impressive place. I hope Tom's going to talk about that some today. Tom's also a noted philanthropist. He's chair of the Thomas and Stacy Siebel Foundation, which provides support for a number of areas, including energy solutions, bioengineering, stem cell research, and a number of other worthy causes. Princeton has been a beneficiary of the foundation. One of the signature programs of the Siebel Foundation is the Siebel Scholars Program, which provides fellowships to the most talented students in the world's leading graduate schools in business, computer science, and bioengineering. And we have some Siebel scholars right here today. I'm proud to say that Princeton is one of those schools. It's also very recently established the Siebel Energy Institute to promote cutting-edge research in energy solutions. And I'm also very happy to say that Princeton is part of the Siebel Institute. Just today, we announced the Thomas M. Siebel Professorship in the History of Science here at Princeton, which supports work in the field dedicated to finding the connections between the sciences and the humanities, something that we do very well here at Princeton. I'm happy to say that Angela Krieger, the first chairholder, is with us today. The gift will strengthen Princeton's ability to understand how scientific ideas have been developed in the past and assess their impact on the future. But for now, to tell us more about his ideas, please welcome Tom Siebel to the podium. Tom?
Thank you, Vince. Good afternoon, everyone. It is my great honor to be back at Princeton, and I propose to talk a little bit about the process of thinking about business formation. Hello, Emily. Nice to see you. And so, just out of curiosity, how many of the people represented here are in engineering? Certainly you guys. Okay. And how many computer scientists aside? Okay. Okay. So I have spent 4 decades, I'm in my 4th decade now in the information technology business, and I've had the opportunity to play the game at a reasonably high level. And I've had the opportunity to interact with people who many of you know and many of you read about, and worked with Gordon Moore and Larry Ellison and Bill Gates and Steve Jobs and a lot of interesting and talented people. And so I'm very, very, very fortunate. And I want to talk about, and kind of my background. I want to talk about the process of business formation and how I've thought about these things, what the process of planning has been, and what the outcome has been. And I think that a lot of people, particularly on the West Coast, and particularly when you get into these bubble economies, that we you used to see about every 15 or 20 years. Now we see about every 8 or 10 years, and we're kind of in one right now. Believe that the process of business planning is something that kind of takes place in a weekend in a dorm room, and you start the company on Monday. And I guess sometimes that works, but not very often. If you look at the statistics in terms of software companies that have been founded since 2003, I forget what the actual number is. I think it's 34, but it's 7/100% have a market value, private or public, over $1 billion today. 7/100. Okay, so I was involved in the formation of a company called Oracle. Turned out to be a pretty good idea. I think they have revenue today of about $40 billion, and market cap of a couple $100 billion. And then a company called Gain Technology that I'll talk about. Siebel Systems was a company we founded in 1993. It was a very rapidly growing company. By 2000, we employed 8,000 people in 29 countries. Had a market capitalization of $53 billion. And this is hard for you to imagine, but this is back in the days when $53 billion was a lot of money. And then in 2009, we started this company called C3 Energy. But each of these companies, I mean, there was between 4 to 6 years of work that went in before they started. So that's what I really want to talk about. And so I am a product of the University of Illinois. I'm a public school kid. Okay. I studied history as an undergraduate, specifically history of science. It was my area of interest. And then went out to work and came back and was in the business school. Went to the business school so I could learn the languages of commerce with the hope of being able to play the game at a little bit higher level. The languages of finance, the languages of accounting, the languages of management, the languages of production and operations research. And so that I could, perhaps play the game. And I remember when I was walking around the University of Illinois Student Union bookstore, I ran across a book published by the MIT Press. It's actually an anthology, that contained a paper by this person by the name of Daniel Bell, who was a sociologist from Harvard, and he was a Marxist, interestingly enough. But Bell, in this idea, he had this idea of the coming post-industrial society. This is written in the 70s, okay? So this is before the mini computer. This is before the personal computer. This is before the internet, okay? And this guy, in other words, the 70s, what are we doing in the 70s? We're building highways, we're making cars, okay? We're kind of, storming through the Industrial Revolution is now raging, right? Okay, and he suggested that there was going to be a fundamental change in the structure of the global economy, okay, based around information technology. Okay, and there's a couple of essays. This has been written in essay format. There's a anthology published by MIT in 1979 called The Information Age, and this is the second to last paper in that anthology that I recommend to you. Okay, and he kind of looks through the evolution of economic structures from like pre-agrarian to agrarian economies, to industrial economies. He talks about in each of those kind of what are the resources that are the most scarce, the resources that are most dear. And, when you get into, agrarian economies, it tends to be forms of natural resources. And then you get into industrial economies, it gets to be various forms of capital. And he suggested that there was going to be this post-industrial society in which the availability and accuracy and timeliness of information would become the most precious resource. And he suggested that all of the consequences of that were going to fundamentally change the structure of the global economy and fundamentally change the way that we work, the way that we entertain ourselves, the way that we communicate, the way that we do everything. And I found that quite inspiring. And I said, this is a game that I would like to play. And so there's a University of Illinois is divided by a thing called Green Street that Vince knows very well. And there's like south of Green Street, which is where all the non-engineering stuff is, which is where I had always lived. And there's north of Green Street, where all the engineers are. And so I wandered off north of Green Street and started taking some classes and in programming and operations research, and found that very fascinating, and managed to, by some subterfuge, get admitted to the graduate program in engineering in computer science at the University of Illinois. And I did my work in relational database theory, which was kind of a new idea that was spinning off out of IBM Santa Teresa Labs. There's a guy named Ted Codd, who was working on a project called System R. And the idea behind relational database theory, as you guys well know, is this was basically the application of set theory to the problem of information storage and retrieval. And it offered some, once you get into it, it seemed to offer some very, very significant economic benefit. And so I thought I would develop some expertise in that field. And so I did my thesis, I think, in performance evaluation of concurrency control algorithms for distributed database systems, which is kind of in the neighborhood of what you're thinking about. This was highly distributed stuff. And then one day when I was getting ready to graduate, in the way they had a thing called DCL there, that thank goodness they don't have anymore, which was where they built a computer called ILIAC, which is a pretty important computer when you get into the history of this business. And there was a phone message there to call Oracle Corporation. And so I called them. I'd never heard of Oracle Corporation. Nobody had. If you wanted to be in the relational database business now in 1983, you would go to work for Univac. Sperry. They had a product called Mapper. IBM, which is working on a research project called System R. And yet I got a call from these guys at Oracle, and I went and visited them and met with a guy by the name of Bob Miner in California and Larry Ellison. And they were about 40 people at the time, and they seemed like very bright guys. And so I decided to throw my hat in with these guys and see if we would make a go for it. And it turned out to be a pretty good idea. And so we took that business from 1983 to 1990, do about $1 billion business. I think we had 10,000 employees, and we had pretty much established a market share. And I kind of came up through the field and worked in technical support in the field, and then went into sales, and then ran product marketing and product line marketing. And when I left, I ran a big bunch of sales and marketing worldwide. And if you think about, as of the end of the 80s, getting into 1990, now we had applied, so now your personal computer era, as you think about it, is just kind of starting. Mini computers are pretty well established. But we had really applied information technology, say, over the last 20 years to change a lot of business processes. General office automation work, manufacturing processes, accounting system, human resources. It was almost inconceivable that you could not conceive of closing the books of a company like AT&T without a computerized accounting system. And so we changed a lot of business processes. And yet the business processes of sales, marketing, and customer service, as of 1990, really were largely untouched by information technology. And if you believed in this thesis that Daniel Bell had put forth, you believed that that was kind of inevitable, that these business processes would be changed by sales, marketing, customer service. And so when I was at Oracle, I built some systems there that kind of changed the way they do business in terms of applying information technology, communication technology to sales, marketing, customer service. And it was a system we called OASIS, the Oracle Automated Sales Information System. And there was lots of interest in this system. People were coming through from a company called Businessland that most of you here will not remember, but that was a big deal in 1990. Rome, IBM. And a lot of people are coming through and lots of interest in the system. And so I went to Larry, who was then in the application software business, and said, Larry, I think there's a market for this. We should, I'd like to start a division and take this. And so I spent 3 years building the system at Oracle and deploying it. And it made a material contribution in the ability of Oracle to be able to take the market. So I took the idea to Larry, and he thought it was a harebrained scheme, and he had no interest in it. So I said, okay, see you later, bye. I'm going to go start this company. And the way things work, I got involved in thinking about that, and a headhunter called, and I got recruited to be. So this is the only kind of random event, okay, that happened. Random events are good. As I thought about starting companies. And I got called to be the CEO of this company called Gain Technology. It's actually originally called Cayenne Systems. I renamed it. What we did there was 1990, 91, 92, believe it or not, we built the first multi-user development environments to build multi-user applications that incorporated sound, motion, video, text, and hypertext. Now today you all live there every minute. Okay, believe me, in 1990 it didn't exist. Okay, and we were doing this, and the primary application initially it was for distance learning and computer-aided instruction. Okay, and then, but you could see, now you can see the general application of this is, maybe broader than that. One thing led to another, and that was a nice business, employee-owned, profitable business that we sold to Gain, to Sybase, for 10% of the outstanding shares of Sybase in 1992, and that's back when Sybase was a real company. And so then we got back to the real job, which is what I had been thinking about for some years at Oracle, which was tackling this area of sales, marketing, and customer service. Now, if you think back now, it's 1993. And if you think back to 1993, 94, 95, there was a big step function of technology that became commercially available. Small form factor nomadic computing devices. Those were important and they were new. Broad bandwidth communications, high-speed relational database systems, really, really importantly, graphical user interface technology that was commercially introduced at large scale by Microsoft with the advent of Windows 95. And what we did at Siebel is we took those technologies and pointed them at the value chain of sales, marketing, and customer service. So this area that today is known as CRM, kind of customer relationship management, we kind of invented that space. Okay, so we ended up building systems, sales automation, customer service systems, internet self-service systems, product configuration systems, marketing automation systems, marketing analytics systems. We did it for the pharmaceutical industry, the automotive industry, the chemical industry, the insurance industry, the financial services industry. And actually, it was the Siebel, we started in 1993. By 2000, we had 8,000 employees in 29 countries. And even today, I think it was the fastest growing enterprise software company in history. It was the experience of a lifetime. Now, so we experienced, and then, by the way, this is back when, you have to remember, this is now 1997, 98, 99, 2000, and that makes the bubble today look like nothing. Okay, people were writing business plans that, nobody needed profits, nobody needed customers, nobody needed anything, okay? And we were very old-fashioned. We ran a profitable, cash-positive business since the day we shipped a product. And so that was a very old-fashioned idea. In the long run, it turned out to be a good idea. I'm telling you, no matter what you think, okay, to the extent that you're involved in a startup company, when the music stops, your company will be valued by kind of the net present value of the future earning streams, okay? Trust me on this. The music stops. You need to build your company for the day the music stops. The game you play in the information technology business is, there's two games. You play a human capital game, I'll talk about that in a little while, and you play a market share game. Okay, particularly in software, outside of the operating system market. Operating system market is the only exception. I'll talk about the exception first. So in 1980, IBM had 90% of the operating system worldwide. Today, Microsoft has 90% of the operating system worldwide. So that's outside of that, the market leader in every market you look at, the market leader will have 50% share, number 2 will have 15% share, number 3 will have 10% share. In an expansive bubble economy like we are now, where the cost of capital is 0, okay, lots of companies will appear to be successful. They appear to be successful because they got venture funding. Believe me, that is no indication of success. And then the market will turn, the music will stop, and when it stops, the company that is the market leader will be the only company that can continue to generate cash. Everybody else kind of goes out of business. And so between, say, 2001 and 2006, I mean, just thousands of software companies went out of business. You could see through every building in Silicon Valley. They were transparent. There was no furniture. There were no people. But we had done a pretty good job, so we were basically larger than the sum of all the competitors of the world in every market that we were in Salesforce automation, call center, marketing analytics, partner relationship management, field service, in every vertical market, in pretty much every place in the world. And so when the world came to an end, which it did, and the music stopped about 2001, in the next 3 years we generated, I think, $3 billion in free cash flow. Competitors. One of the competitors that I had, a very pesky competitor, was a guy by the name of Larry Ellison. And he had set aside 3,000 people to compete with us, and had 3,000 people assigned for 10 years to take us out. This is this whole innovator's dilemma problem that we talked about earlier. Okay, I mean, the trouble is with 3,000 people in software, you can't do anything with 3,000 people. Okay, that's guaranteeing that nothing gets done. With maybe 30 people, you can do something. Maybe 100. With 3,000, nothing happens. And so 10 years later, you had less than 1% market share, and it's 2005, middle of 2005. Market's still pretty slow. And my assistant says that Larry Ellison's on the phone. And so I picked up and there was just this rancorous dialogue that had been going on for 10 years on like the cover of Fortune magazine between Larry Ellison and I. So I thought, this is interesting. I remember picking up the phone and said, Larry, I assume you're not calling looking for a sponsor for your America's Cup boat. And he said, without skipping a beat, that's not a bad idea, but we need to put the names in alphabetical order. And one thing led to another, and we merged that company with Oracle in January 2006. Hugely successful business combination. Good outcome for the shareholders, good outcome for the employees, great outcome for the customers, great outcome for Oracle. And what's perhaps one of the most satisfying things from my perspective, of the scores of companies that Oracle has bought over the years, Sun Microsoft, PeopleSoft, J.D. Edwards, I mean, I don't know how many companies they bought. It might be 100. Siebel's the only brand that they still use. So we built some brand equity. Okay. There's another side of my life where I do some philanthropic stuff. And we started an organization called Siebel Scholars. And the Siebel Scholars, we have, I think, 18 schools of graduate schools of bioengineering, computer science, and graduate schools of business, where each year the dean will pick the top 5 students based upon academic merit and leadership, and they receive a $35,000 award. And they become part of the Siebel Scholars community. Today, I think there are 1,000 Siebel Scholars in the world. And these are from, Tsinghua in computer science, and Princeton, and Harvard, and in business, and Chicago in business, and Johns Hopkins in bioengineering. So you can imagine if you're the top 5 at one of these institutions, you're probably pretty smart. And we get together every year for conferences, and we've tended to do conferences that's something that we find interesting. For example, in 1999, 2000, we had a conference at the University of Chicago on nuclear proliferation. We had Al Haig, Bob Gates, John Major, and Zbigniew Brzezinski, and talked about nuclear proliferation for about 3 days with, I think about 100 Siebel Scholars. I mean, how fascinating do you think that was? I remember at MIT in, believe it or not, October of 2001, okay, a month after the event, this was a year in the planning, we held a conference on the threat of global terrorism at MIT with Benjamin Netanyahu and Norm Schwarzkopf. And if you don't remember Norm Schwarzkopf, he's the one who prosecuted the Gulf War for our side. And then when we get about the time we get to 2006, and as I looked at the U.S. energy policy, as far as I could tell, what we were doing was, kind of occupying all the oil fields in the Middle East, and that was the energy policy. And it didn't seem to make a lot of sense. And so I had some time on my hands, and I started to come out to places where, I had some friends, and I'd come out and talk to Emily at Princeton and Steve Pacala and Vince, and I would go to Berkeley and talk with Steve Chu and Arun Manjadar and Shekhar Sastry, and go to Illinois and talk to Angus Rocket, and go to Stanford and talk with Lynn Orr, and try to learn everything I could about kind of the economics of this problem. We talked about, whether it was the economics of energy production, climate change, and tried to learn a little bit. And we kind of extended that idea, and then we kind of pointed Siebel Scholars that direction. In 2007, we had a fascinating Siebel Scholars Conference at UC Berkeley. It was hosted by Bob Bergeneau, who's the chancellor. We had the Secretary of Energy there. Steve Chu was there. He wasn't Secretary of Energy yet, but we had Spence Abraham there, who was a former Secretary of Energy. Carol Browner, who was former and future director of the EPA. Sam Donaldson hosted it. Myron Ebel I think he's from Harvard. Dan Esty from Yale. Ben Lieberman from the Heritage Foundation. John Meacham it was the editor of Newsweek. Angus Rocket from Illinois. And Jerry Taylor from the Cato Institute. We talked about energy and climate for 3 days. Fascinating discussion. And the story I told earlier, when, as I do all these, we've talked about U.S. criminal justice system, nuclear proliferation, class warfare in America. These are the kind of topics that we address. And I try to balance the argument, so that there's people from both sides. And so I had kind of the tree huggers on one side, Carol Browners and Dan Estes of the world, and Myron Abel, and then we also had someone from Heritage Foundation, Ben Lieberman, and Jerry Taylor from Cato Institute, from the right. And it turned out that both these guys are like Princeton alums. Okay, and what I didn't, and they had their, their orange ties. I mean, the whole thing was going on, and I didn't equilibrate for IQ, and I think these guys had about 20 IQ points above everybody else on the panel, and they were intellectual bullies. They really were, and they just pommeled the rest of these guys. So it actually didn't turn out, I was hoping for a more balanced dialogue. I mean, if you were in the audience for 3 days, you would have concluded that there is no climate problem, there never will be a climate problem, and if you think there might be a climate problem, you're really stupid, okay? Which is not really what I wanted to happen, but so that one didn't work out quite as well as I had hoped. But it was, Princeton made its mark on that one. Then we had a conference on water at Northwestern that was fascinating, which were experts on water. And then we had a conference at energy at MIT that was hosted by Susan Hockfield, the president of MIT. Steve Pacala was there, as I recall. Jim Rogers from Duke Energy, Tom Friedman from the New York Times, Doug May from Dow Chemical, and it was a fascinating discussion on energy and climate at MIT. And then I assembled about 50 people from around the world out to California, and we met in the spring, summer, and fall of 2008. And these are people from founders of Siebel, people from Oracle, SAP, Intel, Juniper Networks, the energy team from McKinsey & Company, people from Accenture. And we spent spring, summer, and fall talking about climate, information technology, communication technology. And back then, we were still thinking about this. This was still a kind of a philanthropic discussion about what can we do philanthropically that might have an impact on this dialogue. And Emily was involved in some of this stuff, and so was Vince and Steve Pacala. And once we got, or the precursor to this discussion, and then when we got near the end of it, Steve Ward was there. Steve Ward was the CIO at IBM. We had Sean Coyne there, who was the CIO at GE Power and Toyota. So there were some knowledgeable people. And it became apparent by the end of the year that perhaps the best way to have an impact on this discussion was not through a philanthropic effort, but through a private sector response. And so we decided to form this company. So then it kind of started forming into working groups to think about product and technology and strategic alliances and what's the company of the future look like. And by December, the decision was made to start this company called C3. And C3 kind of C related to the carbon atom. And back then we were kind of talking about the idea of kind of measuring, mitigating, and monetizing the issues associated with carbon. So that's where C3 came from. And so I sent out an email on Friday. We raised $20 million by Sunday, and the company was founded. And then we formed a network of people and organizations that we kind of mined for the next few years to try to figure out this space. Okay, now, what's rule number 1, 2, and 3 of an information technology company, okay? I guarantee you it is a human capital game, okay? Whatever idea you're thinking of, it won't work, okay? Whatever market you are thinking is there, it is elusive, it will change, okay? And fundamentally, it's a human capital game. It is your team against their team, and it's whether you have the human capital to figure it out, to be able to change, to be able to deal with adversity, ephemeral markets, okay, and insurmountable technology problems. And so when you think about human capital, the first thing you do is think about assembling a board. So I rang some doorbells, and we developed a pretty good board. Ed Abbo ran all software at Oracle, Princeton alum, MIT alum, used to run all software at Siebel. Rick Levin at the time was in his 17th year as president of Yale. Shankar Sastry, Dean of Engineering at Berkeley. Spence Abraham, Secretary of Energy. Mike McCaffrey, Princeton alum, investment banker, chairman, I think, of Rhodes Scholars. Really smart guy. Mayo Shattuck, chairman of Exelon. Pat House co-founded Siebel Systems with me. Condi Rice is Condi Rice. Steve Ward was our largest customer at Siebel. He was the CIO at IBM. We had a 100,000 user system there. That was a $1 billion project and a very, very complex project. And then we went about assembling a team of kind of tried, tested, and proven executives, all of whom had, a couple of Super Bowl rings. And in one company or another. And then we thought about this problem. And so now, remember I talked about when I was thinking about the mid-90s, about sales, marketing, customer service, I said, well, there was a big step function of technology that had come available. Let's fast forward to 2009, okay? And we have a new step function of technology, okay, that's available. So we have a new set of tools. And what would these tools be? These would be, well, cloud scale computing, machine learning, analytics, okay, hugely importantly, okay, social human computer interaction models, okay, and we said, okay, let's take that step function of technology. So I've spent my career trying to do easy things, okay, rather than hard things. I just kind of take the tools that are available and point it at a problem. So we basically took that step of technology and pointed it at this value chain. So this is the value chain associated with energy production, transmission, distribution, okay, metering, and delivery. And if you look at the structure of this value chain, it's kind of built with really, early 20th century technology. Thomas Edison would recognize it. At one end, you're boiling water, okay, somehow. You're spinning a turbine. You're stepping up, they're using a transformer to step up the voltage and distribute the stuff over long distances at high voltage for reasons that all you engineers know, so we don't need to get into. Okay, and then we step it down to medium voltage. It distributes over medium distances. It goes to a meter. It used to be an electromechanical meter, and then we deliver at low voltage, like 220 or 440, to the consumer. That's it. And that value chain delivers something like 22 billion gigawatts of energy a year. And it is, I think this was identified by the National Academy of Engineers as the most significant scientific achievement of the 20th century. And it is primarily made out of kind of lead, acid, and copper, okay, and it's very brittle. So the way that it works until the lights go out on Nassau Street. And the lights go out on Nassau Street, and somebody calls whoever it is here, Northeast Utilities, and says, the lights are out. And then they send trucks out, and with people with voltmeters, they climb telephone poles and go down manhole covers to find devices that don't conduct electricity, and then they keep replacing boxes until the lights go back on. That's pretty much how it works, believe it or not. And now, these businesses are pretty much run as separate silos: generation business, transmission businesses, distribution businesses. And within those, you have these information systems that do things like generation management, customer care and billing, meter data management, outage management. And these are classic enterprise information systems that come from companies like Oracle, Siemens, GE, that handle reasonably large amounts of data. And because they're enterprise, and this has been driven over this whole period by the benefits of Moore's law that we don't need to get into here because you're all experts at that. Now, for those of you who had experience in enterprise information technology, you know that all these systems really don't want to talk to each other. There's lots of reasons for that. Okay, some of them because they're designed not to talk to each other, but others it just kind of happens that way. Very difficult to communicate across systems. Now, this information, this value chain, this decade, is being upgraded in a manner so that all the devices in the value chain are becoming remotely machine addressable. Okay? And so if it's a remotely machine addressable, this means we can remotely sense its state in real time, right? Like a smart meter. And so we don't need to send a truck out once a month to have somebody write down the 6-number sequence. We can, in real time or near real time, see what it's doing. But it's not just the meter, it's the vibration sensor on the nuclear reactor, the transformers, the substations, the single phasers, the meters, the thermostat, the variable speed in the home, the variable speed fan at Walmart, all that stuff is being censored. Okay, so now and the amount being invested this decade, I'm not making this up, okay, in censoring this infrastructure is $2 trillion worldwide. Okay, let me help you out. That's a big number. Okay, and for those of you who were involved when the internet was developed, say 94, 95, 96, 97, I can assure you nobody was thinking about spending $2 trillion on that infrastructure. Okay, so now so this begins to look like in the future, like by 2020, basically a fully connected sensor network. And so this is where Metcalfe's law applies. So Metcalfe's law, I don't know if Bob Metcalfe went to Princeton or not. Bob Metcalfe is a guy who came out of Xerox PARC, invented a thing called Ethernet, turned out to be pretty useful, and formed a company called 3Com. And Metcalfe's law basically says that the power of the network is a function of the square of the nodes that are on the network. And so we have kind of Moore's law meets Metcalfe's law here is what is happening in like the next 6 years worldwide. This is a huge technology upgrade. Now, so what we have done is we have developed, we've spent the last 7 years and a couple $100 million develop a technology foundation to address this opportunity, okay? Enabling a grid operator to take the union of these data and, by the way, the amount of data increases now by like 4 to 5 to 6 orders of magnitude. So if you read a meter once a month, that's 12 meters 12 times a year. If you read it every 15 minutes, it's 32,000 and change. I forget what the last 3 numbers are, 500 and something. One of you guys will know it on the top of your head, I'm sure. Okay, but it's 4 orders of magnitude. Okay, and so none of these systems can handle those kind of data volumes. Now, so what we've done is we've built a technology foundation that allows a grid operator to take the union of these data, aggregate the data into a unified federated cloud image, subject the data to an analytics engine, kind of like a Palantir-like analytics engine. Everybody familiar with Palantir? They're the people that, if you have any friends in Yemen, they know you really well. Okay, they're the people who are tracking all your cell phones. But basically an analytics engine. There's batch and streaming analytics on these data, and then we apply a science called machine learning to extract all the meaning out of these data, and then we manifest, basically looking across the entire value chain in real time. We provide a family of what we call grid analytics that do everything from like AMI operations to volt var. If you can balance volt var, you know, resistive voltage, if you balance that across the system properly, you have to generate 7% less energy, less power, 7% less coal gets burned. Hey, that's a big number, okay? AMI operations, if you can look at all of the signals in real time, you can kind of reduce billing errors, predictive maintenance. You have hundreds of millions of assets in the grid infrastructure. If you process all the signals and you look at everything in real time, you can tell the grid operator what devices are most likely to fail next and why, so they can replace those devices on a scheduled truck roll rather than 2 in the morning when somebody calls from Nassau Street, okay? And the economic benefit of predictive maintenance to a utility operator is order of like $20 a meter a year. If you have, in the case of Exelon, 10 million meters, this is significantly non-zero. Revenue protection, huge problem, revenue protection. This is a euphemism for theft. Okay, in the United States, like right here in River City, about 1.5% of energy that's generated is stolen. Okay, so for Commonwealth Edison in Chicago, this is $200 million a year. You get into Sicily, it's like 30%. Brazil, it's everybody. Okay, so if you can use analytics to tell a utility operator who's stealing energy and how they're doing it. Okay, now the reason, what's the benefit of that is everybody else has to pay for it. And so this is what we've done. So we provide this stack, and the economic benefit of this stack is about $300 per meter per year. Again, if you have like 8 million meters like Exelon, it's a pretty big number. If you have 70 million meters like, say, Enel in Italy, it's even bigger. So we're dealing with economic benefits on the order of, in some cases, in the case of Enel in Italy, I think it's $6.2 billion a year in recurring economic benefit to the consumer. Okay, what's another economic benefit? Another benefit. You can cut the greenhouse gas footprint of this business process about in half. Okay, so this is what we've done. We've been building out the stack, and now we're installing these products today, or have installed these products today at kind of these utilities around the world. Some of these are pretty big. So the United States, there's about 100 million meters in the United States, 3,250 utilities. Okay, and now in Italy, and now in Rome, they have 70 million meters. Okay, GDF Suez, they operate in 40 countries. GDF Suez has 80 million meters. So these are companies roughly the size of the U.S. market. And so these are very large systems. I'll talk about kind of what's interesting about this. So here's a case point. Baltimore Gas and Electric, they have 2 million smart meters. It's part of Exelon. And there what we did in about a 6-month period is we aggregated kind of 12 information systems that were never designed to communicate with one another. We aggregated 35 billion rows of data into a 10 terabyte cloud image. Okay, we processed these transactions on the order of 800,000 transactions per second. 800,000 transactions per second. Okay, the reason that I underline that is that's about 50% faster than any published benchmark that's out there from Netflix, Amazon, or Google. That's a big number. And we use this for AMI operations, and we've identified order of 1 million. We've eliminated order of 1 million billing errors. Revenue protection, where we've identified, we eliminated like 80% of the revenue theft, and then kind of general purpose energy intelligence. So this is what AMI operations does: is manage the whole health of the network infrastructure, which when you deal with hundreds of millions of sensors out there, it can get pretty difficult. And we apply, I think, 90 different analytics to do this. Revenue protection is applying analytics to identify who's stealing energy and how they're doing it. How do you do that? Okay, you look for anomalous load, you look for intermittently connected meters, you look for meters that are running backwards at night. Okay, I mean, there's lots of ingenious ways that people steal energy. And we can do this with about, I think we have order of 78 different algorithms that we run, looking for consumption on an active. Okay, house is vacant. Okay, here's a simple one. House is vacant, account has been closed, meter keeps spinning. Maybe there's a problem here. Okay, now that doesn't seem very difficult. What do you need a computer for? Okay, you can do this on the back of a cocktail napkin, right? Unless you need to do it across 70 million meters. And all those 3 pieces of information are in 3 different information systems in 3 different departments that don't talk to one another. So then it gets kind of hard. Economic benefit of this application is about $20 million a meter a year. Economic benefit of this application across all of Exelon is $383 million a year. Now, I've been in some pretty interesting conversations in the information technology business. I haven't been that many where you're talking about hundreds of millions to billions of economic benefit a year. And now, here we're deploying right now across 44 million meters. There are 50 million meters in Europe today. Okay, and so we're deploying actually 5, but I'm just going to talk about 2 applications in Spain and Italy. This is an application that these people, this is a 100 billion euro business, 75,000 employees, and this says 61 million customers globally. I think it's a little bit more than that. These guys are kind of the master of the universe at this is better than, where they currently operate in terms of reliability and cost is better than the best decile in the US. and this is where they want to go. This is the project that we're involved in with Enel. It's now the middle of February, so hopefully Ed Abbo has got this thing under control because it's got to be done pretty soon. And here we're aggregating information, 7 trillion rows of data, 7 trillion rows of data from 13 disparate data sources into an 800 terabyte cloud image, and we're processing the transactions at 800,000 transactions per second. We're doing this this has been on the Amazon cloud, in data centers that are in Ireland and Seattle, 500 virtual machines, 300 Cassandra nodes, for those of you who track that kind of stuff. And the economic benefit of this application, predictive maintenance. I've talked about what this is going to tell them what's going to break before it breaks. Revenue, and that's putting a real-time risk index on hundreds of millions of assets in the grid infrastructure. This is dealing with weather, who's the client, okay, weather forecast, load forecast, tell you what's going to break next. It's an interesting problem. Now, when you look at this problem from an information technology perspective, there's kind of what appear to be two difficult problems. One is, how do you aggregate all these data from disparate data sources into a common data image and keep it current? Okay, for those of us who've been wrestling with enterprise systems for the last few decades, I can tell you this is a really, really, really hard problem. Okay, the second issue is, if you can do that, how do you process the data, okay, at the rates that you need to process to keep up? I mean, in the case of Exxon, you're dealing with a 800 terabyte cloud image that grows at the rate of 300 gigabytes a day. I mean, this is pretty fast, right? I mean, it's hard to keep up with. Okay, well, once you get beyond that, and it took us about 5 years to get beyond that and figure out how to solve that problem, you find out this is like a video game where you get to like the 11th level and you're in a different place. Well, it turns in you find that you have a machine learning problem. And I don't know how many people are thinking about machine learning here. Okay, but I mean, this is a fascinating field. Okay, and machine learning is about, we all know what algorithms are. Okay, an algorithm, we can have an algorithm for, it's just a series of steps. How do you drink a water? Pick up the bottle, take up the top, swallow, put the top back on. That's an algorithm, right? Okay, and, so computers they're kind of nice because they do algorithms, series of steps real fast. And sometimes we can do things, we do enough of them in meaningful ways that does something interesting. Well, machine learning is about algorithms that are self-learning, that get better and better every time they run. And it is a fascinating field. It is equally fascinating as human computation that we were talking about earlier. Eversource, this is not New Jersey. Who's the utility here? Who's the utility operator? PSE&G? Are they part of Northeast Utilities?
No, independent.
Okay. Eversource is another one. Okay, so this is what we're doing in this space. AMI operation, I'll move this real quick. Already talked about revenue protection. Predictive maintenance. Identify devices before they're going to fail. Grid investment planning. This is the reverse of grid investment. Duke is investing $12 billion in capital in the next 2 years. Okay, this allows them, if you know what devices are most likely to fail next, you can allocate capital with surgical precision. Load forecasting for demand response purposes. Demand response analytics. These are big, complex problems. Generation analytics. For those of you with outage analysis, prediction and restoration, is that of value around here? I think so. Voltage optimization, we talked about the economic benefit of that. 8% less fuel that you have to burn. Grid cybersecurity, okay, this is a very interesting field. This is now the intersection of kind of these perimeter security systems. And we look at these perimeter security systems from, whether it's, FireEye Mandiant, or what's the Hewlett Packard offering? Symantec, McAfee, okay, that are basically looking at perimeter security. They're telling you, okay, who's trying to penetrate, okay, and they basically look at a big database of signals and say, hey, this looks very much like a signal that we're used to seeing coming out of Syria or China, or it's a piece of malware that, it's basically they're doing pattern recognition. Now, so you have people who are in charge of grid security who are down in some sub-basement looking at green screens, looking at this gibberish coming. Imagine what it looks like in a denial of service attack, right? Where just this gibberish is coming across the screens. Well, what does that mean? Well, if you can tie this all together, you could say for every one of these signals, it's actually what customers are impacted, what's the single point of failure, what portions of the grid are impacted, so it allows you to prioritize these events. And so for those of you who think about cybersecurity, it has a very significant impact. And actually, we'll be talking about this before Congress, I think, next Wednesday. So I'm going to skip over this. We also do the customer engagement. This is a very interesting part. The utility industry is kind of firmly entrenched in like 1960s in their customer engagement model. They actually use mail. Anybody get mail at their house? Okay, and call centers. And so, I don't think this is how people are going to integrate, could you imagine using mail and a call center to like buy something from Amazon? And so we're kind of bringing the securities into the utilities into the 20th century with kind of Uber and Amazon-like technologies for enterprises, small and medium businesses, and residential customers. What's interesting about these problems? The data sets are staggering. The analytical problems are daunting. The processing requirements are scary. And the human-computer interaction problems are, as of yet, unsolved. Okay, that's probably the most interesting part, is the human-computer interaction problems. Now we're applying the same stack. Really what we've built is we've built a stack for building cyber-physical systems. So we have this canonical data model that allows us to aggregate all the utility data into one thing, into a combination. We do the same thing for oil and gas. What's the difference between the oil and gas industry and the utility industry? Well, the people are a lot smarter, it's a lot bigger business, and they invest about $500 billion a year in capital every year. And this is a pretty big business. So we can apply the same technology to bring the same efficiencies to this business. The value chain has remarkable similarities. We'll kind of roll up the data into a common data image, okay, process the data, and then manifest these, what's the value of predictive maintenance? Well, at any given point in time, 8% of the oil production facilities are down because some devices failed. That's like order of $350 million a day. So we do it in oil and gas, drilling and risk productivity. So who are we talking to? Occidental Petroleum, Chevron, now Saudi Aramco. Well placement and completion, integrity and health, predictive asset maintenance, production optimization, hydrocarbon loss accounting, demand forecasting, refining analytics, and then fuel station analytics. So now, talk a little bit about machine learning. We've invested a lot in this, and this is kind of this is a fascinating field. So imagine that you have 78 algorithms that you're using to determine whether somebody's determining theft. Do you have anomalous load? Is the meter intermittently connected? Okay, is it running backwards at night? But you have 78 algorithms. What do you do with 78 of them? Well, what you do is you map this stuff in 78-dimensional space. Okay, and so then, you have a training set where in a 78-dimensional hyperplane, things will cluster into theft or non-theft. And this is what these machine learning guys do. And they have these perimeters, so basically when the next data point comes through, if it falls into theft domain or non-theft domain, you can pretty well tell, unless it falls outside of the two, and that's where it needs to correct itself and adopt that, and basically change that parameter in n-dimensional space the perimeter in n-dimensional space to be able to take that new data point. And these things get better and better at what they do as they operate. And so we have a team of data science guys. I recruited Siebel Coulter from the faculty at Carnegie Mellon. He's probably the foremost expert at the intersection of machine learning and power systems. Recruited Hendrik Olsen from the faculty at UC Berkeley. These other guys are all Stanford guys. It's at Medi. He's also from a PhD from Berkeley. Now we're very pleased that we're on the institute side, on the foundation side. We funded basically a reasonably large-scale development project and we're very pleased to have Princeton very much involved in the leadership of this. Ecole Polytechnique, University of Tokyo, MIT, Carnegie Mellon, the University in Torino, Berkeley, and University of Illinois at Urbana. And this is kind of the first large-scale multinational effort that we're aware of to advance the science of machine learning in a big way. And all of the work that gets done here goes into the public domain as non-exclusive royalty-free licensing that's available to everyone to use. So this, I think in 5 years, we're going to advance this science in a big way. Now the interesting area, and this is the last slide. Okay, what we've really done, okay, is we've developed the hard work that we've done, the interesting work that we've done, is we've developed a platform for delivering large-scale applications related to this area that we call cyber physical systems. Okay, so this is kind of what they call the Internet of Things. So this is the interaction of people, of sensors, and of data sets. Okay, and you can see, the application. I mean, this is, kind of what the future is all about. And we think that, this stack now we're talking about applying to financial service problems, healthcare problems. All you need is basically replace the canonical data model. And in every case, in every industry, you have an XML standard that you can use. HIPAA in healthcare, WITML, PRODML in oil and gas, OpenADE in utilities. And so what we're now developing this is a general use platform for the development of large-scale cyber physical systems. And what we're going to do with that, we're not certain, but we know it's a lot bigger than anything that we've done yet. So, of the various adventures that I've been involved in, this is by far the most difficult, okay? By far the most challenging, by far the most interesting, and I think, it's, I think that it's highly unlikely that at the end of the exercise that we will not have made a contribution to the dialogue. And I think we're going to make a significant contribution to dialogue. I think our objective is to establish and maintain a market leadership position in this market worldwide. Okay, if we succeed at doing that, this will be a very important company and the world will be a better place. So that's how we've thought about, what we do.
Thank you, Tom. Can we take questions?
Absolutely.
So I think we have time for a few questions. Any, Emily?
Hi, Emily.
Hi, Tom. That was really great. So question for you, because clearly a lot of this requires a lot of computing. Computing takes energy. Has your team actually sat down to figure out the net energy benefit to, if you were to deploy this worldwide, in terms of the amount of energy that it takes, assuming normal supercomputers that are being used today?
Well, the answer is we have not. Okay, I think if we did it, it would be minuscule compared to the amount. I mean, we can drive 20 to 30% efficiency out of the grid. So in the case of Japan, this is like, we think there's 100 gigawatts there that we can take out of Japan alone. And so it pales compared to what we're using. Now, as it relates to compute infrastructure, okay, the one thing that we're absolutely certain of is, these supercomputers are useless to us, okay? And computers, as we used to know them, are all useless. Everything that we're doing today are basically on, 2,500 Dell computers, $2,500 computers in the cloud. okay, and we'll deploy, hundreds and hundreds of virtual machines. And the cost of this stuff is basically zero. I mean, it's fascinating. The cost of storage is zero. The cost of compute capacity is zero. We're involved, I'll talk about Enel very briefly. Enel, again, $100 billion business, okay, with data centers in 23 countries, 1,700 enterprise applications, and they will close all their data centers in 2 years. This is the largest IT transformation in history. So we haven't done the energy calculation, but I mean, it's orders of magnitude.
Yes, I mean, it should only be a couple of percent.
Yeah, we haven't done it, but it's orders of magnitude.
So can I ask a question?
You bet.
Okay, so the other thing I was wondering about is you say that you could, well, it sounds like, well, actually, I have two questions. So two more questions. One is about the predictive maintenance. So as an engineer, I know it's extremely hard to predict when something will fail. You can predict statistically based on experience when something will fail. Is that what you mean by predictive maintenance? Is basically that on average you'll say probably something?
Yeah, it's looking at basically, and I can get Zico on the phone with you, but it's looking at all the devices, all the transformers of this type, okay, that exhibited this types of characteristics. Okay, if they've failed within this period of time, or some percentage of them have failed at this period of time. So it's not with certainty.
Right.
Okay, but we can think that, if we have one transformer that we installed in 1960 and one we installed yesterday, okay, one has, distilled gases, that are significant, one has none, okay, one is connected to the hospital, the other is connected to the liquor store, okay, and one is in the Alps where there's going to be a big weather event, and the other is in Sicily where there's no weather. Where do you have the biggest problem? Well, it's going to be the higher here, and mathematically we can put some certainty around the fact that it's significantly higher, that this is more likely to fail than this. Now, all these guys are absolutely blind to that. So now, how precise that number gets is going to be pretty interesting, and we're about to find out at very large scale.
Another question.
Yes, sir. What's your name?
Jerry.
Jerry, hi.
Yeah, hi. So as a student here who's interested in entrepreneurship, specifically on putting solutions for enterprise-wide systems, I'd be interested if you spoke a little bit more about your time while you're at Oracle, but thinking about starting Siebel systems and the idea behind that. Like, were you testing the market while you were in your role there at Oracle for the formation of the Siebel? And were you so you're testing? Were you like talking to people, or was this just an idea that you were forming in the back of your head, and you were just going to go out and do it?
The idea of Siebel?
Yeah.
Yeah, no, that's something I thought about for some years at Oracle and then built it. Okay, now, I was a reasonably competent graduate engineer from the University of Illinois, okay? And I think that, the best thing I did, okay, was go to work first at Oracle. And Oracle was a horribly mismanaged company, okay? It really was. And what I learned at Oracle was how not to do things. It was a great learning experience. Okay, now I talked to a bunch of people about to graduate here today or graduate, and they're going to work at Google, they're going to work for large research companies, they're going to work for, if I wanted to be an entrepreneur, okay, and obviously I did, okay, I would not leave school and start a company. I would go, people I do not believe are genetically disposed to be great engineers, okay? There is no substitute for experience. To be great entrepreneurs, okay? There is no substitute for experience, for making mistakes, for seeing people make mistakes, and I would go to work someplace. Oracle, IBM, GE, it doesn't really matter, and I would see how it's done, and I would learn. I would develop a network of people. This is a human capital game, and there's more people than just the 3 guys that you know in your dorm, okay? Or people that you know in your dorm, okay? I would really encourage you to think about going to work someplace and seeing how they play the game and having the opportunity to make mistakes, because I'm telling you, starting and running companies is really, really hard. Okay, that's when you stop sleeping. Okay? Yes?
I'm getting a signal here. Maybe we'll take one more quick
Oh.
question, and then we do have a
They're pulling
reception
the plug on me.
Tom will be there, but let's take just one more
One
quick
more question,
and
this
then
young lady.
we'll break.
Following up that, hi, my name is Sharon.
Hi, Sharon.
What are some of your biggest kind of learnings and mistakes that you've learned from kind of making your own companies? Like, what are the biggest issues that you face?
If it doesn't make sense at small scale, it doesn't make sense. Okay? There's a lot, I mean, if you can't do it on a cocktail napkin with a pencil, it doesn't make sense. Okay? The reason that you don't understand it is because it doesn't make sense. Okay? And you have these people that are making it up with volume or at scale or with gibberish. Okay? And if you can't get it down to like a crayon and a piece of paper, it's because it doesn't make sense. And that's the one thing that I've learned. Okay, you got to get it down to if the degenerate case doesn't make sense. We all know that word. Okay, it won't work in volume. It won't work at scale. And that's, I think, the most important thing. So so I have found that there are many things that I don't understand. And the bar for me is like, a lot lower than it is for you. Like, there's a lot more things that I don't understand than you, believe me. Okay, but if I don't understand it, we don't touch it. And that's what I think has been the most important thing that I've learned.
Okay, thank you, Tom.
Thank you all so much.
So, we can't let you get away from here without something orange and black.
All right.
So we have something orange and black. So thank you so much, Tom. Thank you. This is a sort of mind-boggling scale of what the problem C3 is dealing with. But I know if anybody can make it happen, it's you.
We're trying.
So thank you again, Tom. We have a reception set up in the atrium, so Tom will be there. So please join us. Thank you again.